Hello everyone, my name is Chang Liu and I worked with this project with my teammate Yutun Zhao, and we are team 25, and our project name is Spark Power Infectious Epidemic Dashboard for the US. And our goal is that we have a new system design. The dashboard for any infectious epidemic system is an interactive tool designed to visualize the spread of infectious disease across different regions and time. It uses key data points such as location, time, cases, and deaths to generate real-time insights into an epidemic progress. And here we have more diseases, more data, and we can work with any kind of data in that kind of format. And the right one is our integrated dashboard. You can see an overview here. And for our workflow, we started from the original data, and we process it with the time, state, effect, or death number, and after the Kafka streaming, we can process it with Spark stream analyze and batch analyze, and finally we will create map and bar chart with Python eChart toolkits to make to realize the visualization, and finally we do make the code integrations to make our integrated dashboard. And this is our demo here. And this is our integrated dashboard. You can see the US disease map here, and we can slide the bar to see the transition at any kind of time. And we have lots of analyzed map here, and we can put our mouse onto these maps to see some detailed information there. And I will introduce them in the following parts. After seeing the demo, we are going on with the data. We mainly use the US COVID-19 country dataset here, which from the initial reported case until May 12th, 2022. And it has 2.5 million rows of data, and these columns consist of the dates, the country, states, and the number of confirmed cases and deaths. We also use CDC's provisional death counts, which include influenza, pneumonia, and COVID-19, which conducted a simple workflow test to validate the accuracy and functionality of a dashboard generation process. And for the pre-process, we filter and clean. We filter the key points such as dates and so on, and rows where the case and the deaths are missing, those fields are set to 0. We will also generate procedural timestamps for stream. And for the Kafka stream, we use it for the task 1 and 2. Our aim is to transit these kind of static data into streaming format. So we finish the version merge and the Kafka startup, which related with a Rookkeeper, saver, producer, and consumer.
And here's our United States dynamic infectious epidemic map. This map is the dynamic update from the slider moves, reflecting changes in case counts for each state. For the progress presentation, we only have like 20,000 raw data, and now we found more data. We get more various data up to 2 million data. The states are color-coded in real-time basis on the selected data. The map is built using D3, a powerful JavaScript library for the data-driven visualizations. And we found from the government website the GeoJSON data, which is used to define the state boundaries, while the case data is time series based. And the interactivity is achieved by binding the data to the map and updating it based on the user input.
And for the Spark process, we will use both stream and batch. For task 1 and 2, this task is time sensitive and require real-time updates as new data arrives. And for task from 3 to 7, those tasks require in-depth analysis of large historical datasets. And for stream task 1, we group the data by date and compute the sum of cases and deaths for each day. Cases reached 81 million, where deaths approached 1 million, underscoring the severe impacts of the pandemic. The task 2, we used a window function comparing each day's total with the previous days. And we can see that there are 3 time periods which shows significant spikes in new confirmed cases and deaths, which indicates policy changes, new variants, or seasonal impacts. And for the batch part, we use a Spark circle here. We group the data by date, state, and compute the sum of cases and deaths. We divided the total cases by total deaths by total cases. And for some area, more cases with low death rates. They may have higher vaccination rates or effective state-level pandemic response measures. And in the task 4, which shows the first 10 states with the most least cases or deaths, we use a Spark circle which will select and sort. There is no significant changes in the overall rankings. And for the batch, for the total death rates, the death rate in the US represents 1.22%, which is significantly higher than the WHO standards 0.6%. And for the wearable behavior rate increase or decrease, we use this score formula here. And this score in 7 days over 2 flags the abnormal increase or decrease. And both of them surged occurred primarily in period of April 2020, from December 2020 to March 2021, and December 2021 to January 2022. And for the task 7, which is the last one about prediction, we use the reference data as a feature. And we use 2 algorithms here, which is linear regression and decision tree. And linear regression shows some limitations that they underestimates the actual cases and deaths. And decision trees that maybe reference data may not lead to appropriate states.
After all the work we have done, we decided to integrate all the graphs we have got. So here is our enhanced dashboard structure diagram. We consolidate multiple HTML files with e-charts and D3 visualizations, and automated title extraction from chart files for clean and consistent display, and designed responsive layout using the Bootstrap for seamless cross-device compatibility.
And for the conclusion, what we achieved is that we identified and solved key technical challenges, including efficient Spark processing of large infectious epidemic datasets and the integration of complex workflows into a comprehensive dashboard. Our future work includes a switch seamlessly between datasets and visualization of finer green time intervals, and the integration of external datasets could provide deeper insights into factors influencing disease spread. Thank you. That's all of our presentation.